Without further ado, Tibor Beke speaking on Schanuel functors and the Grothendieck semiring of some theories.
Thank you so much. Thanks for the invitation. I'm positively embarrassed to be here in front of these guys. You know, all of you who know so much more about any of these than I do. And I also want to tell you that I'm coming from the direction of algebraic topology, maybe with a slight hint of algebraic geometry, and maybe model theory, if you want to call that. So occasionally when it comes to category theory, I may be the one who reach out to you guys and ask you what you think of something. This is about a particular paper, a single one paper of Steve Schanuel that you probably all read, that really captured it. And I just like to give my take on the proof to begin with, and then some additional flourishes that I added that hopefully I never get to, and I will never have to tell you about. So this is our guy, and Schanuel's lemma, I think he found it when he was still in graduate school, and he formulated this conjecture, a very deep conjecture, just a conjecture that alone will make him immortal in transcendental number theory, as a student of Lang, I believe. And I'd like to add to this list. I know it's more of a mouthful, this last item, than the first two. But I'd like to convince you it's a wonderful thing, and it's one of the few examples of an explicit finite presentation of a Grothendieck semiring, or whatever that is, but it's a reasonably well understood and important category in algebraic topology, maybe in real algebraic geometry. And of course, we all know Steve, and he got really turned on to category theory, I guess, once he moved to Buffalo. But I just discovered something that adds to the depth of Steve. This is an actual student quote. You know, when I die, I like to have something like this on my epitaph. Somebody said something like this about me. Let me not quote you the other student responses on the same website. Some of them said, you know, scream and run away, and others said, you know, this guy made me unlearn all the mathematics that I think I knew, or that I thought I knew, and probably that's a point of pride, right? Anyway, so when I encountered Grothendieck rings the first time, it was the Grothendieck ring of algebraic vector bundles over an algebraic scheme or what have you. And this is the definition that goes back to Grothendieck, so you can't take it away from him. And I could not fit Steve Schanuel's interest in Grothendieck semirings into this definition, and I still can't. And you know, there's also the Grothendieck ring, or if you want to say just the semiring, if you just want to get the positive half of it, of topological vector bundles. This is the degree 0 part of K-theory. To anybody in algebraic topology, it's a very natural definition. It's an instance of Grothendieck ring construction coming from geometric data, but it's not associated to the kind of data that Schanuel seems to be interested in that particular paper of his. And there are lots and lots and lots of Grothendieck rings in mathematics. This is Grothendieck's own definition of the Grothendieck ring of varieties. And once again, you can't take it away that this is an important Grothendieck ring, and this is the right definition. And it incorporates these topological notions, such as an open subvariety with closed complement, the scissors relations, tensor product giving rise to the product. Once again, you just collapse by isomorphisms like before. I actually cannot fit all the puzzle pieces together, but I want to say that Steve Schanuel's point of view, focusing on distributive categories, coming up in just a couple of slides, is still a good one. So this is still not the topic that Steve and I were interested in, and there are so many other Grothendieck rings around where you can ask very similar questions about, are they finitely presentable? What is the semiring part of it? Is the semiring finitely presentable? And like I say, I don't find a common denominator of all these examples, but this is still a very nice and big family of examples when you're interested in distributive categories. So you've all seen this definition before I did. This is just one particular way, very simple-minded one to think about distributive categories. It's strictly the categorical product versus the categorical coproduct in this additional constraint that you need to impose. Something, by the way, where once again I'm reaching out to the experts in the audience, is that, so in this particular distributive category is the categorical product and the categorical coproduct, so you have this canonical comparison map. It all fits together very nicely. But you could ask very similar mind games about a category that has just two symmetric monoidal structures, provided the two symmetric monoidal structures distribute against each other suitably, and one against the other suitably well, in such a way that this distributivity law is coherent. So this is coherent by the universal mapping properties, and so you don't need extra coherence axioms, but I've actually never seen the notion of kind of a ringoid, not a ringoid category, but a semi-ring category. So asymmetric monoidal structure plus another symmetric monoidal structure, tensor product. And tensor product distributes with respect to plus coherently, whatever that means. So you have not more than 17 diagrams that generate all the commutative diagrams of the free object in this category, something like that. Peter May tried to do this in the 1970s, and he got into a lot of trouble. He just didn't get it right. Laplace had related work, but only for the one-sided version, when it's not symmetric monoidal. And if you look at the underlying combinatories of the identities of distributivity, and you try to kind of make them as neat like hexagons and pentagons, so that everything follows, I think it's a hard task. Peter, you were about to say something?
I was thinking of linearly distributive categories.
Whatever they are, what are they?
That would be the wrong kind of thing, though, because the distribution was different. It doesn't duplicate X.
No, it permutes them, that's true. Yeah.
Anyway, so we stick to this kind of very neat point of view, and then the associated Grothendieck semiring is the isomorphism classes of objects on the coproduct and on the categorical product. And I'll tell you in just a sec what exactly a semiring is, but you all know what it is. And this notation is not exactly standard. The K group, so this K is from classes of vector bundles originally. The K group notation is very standard, so I kind of got used to it. And this S is my reminder that this is just 1/2 of the associated K group. Once again, sometimes they write a little plus here or whatever. The big difference is that here you are not interested in adding formal inverses to the plus operation. You just keep the positive side of things. And in that particular article, once again, almost anything that I say is kind of lifted from 2.5 paragraphs of this article. Schanuel calls this the Burnside rig of a category. The reason it's a rig is that it's like a ring but no negatives. It's just the plus side of things, so we nicknamed it rig. I don't think this has become standard. And the reason it
Other people use that term.
Good. I've never seen it elsewhere.
Levere uses it all the time.
Okay, so this tells you something about these subcultures of mathematics. I mean, the algebraists would not call them rigs, but they are completely okay with semiring and vice versa.
Yeah.
I don't know.
Grothendieck added, like, artificially added in the negations. No?
Yes, correct.
So did he do it for a reason, or did he just not have a notion? I mean, everyone knows what a group is, or a ring is. Did he not have it, and he just added it in?
I think it simplifies the thing.
Definitely.
He was interested in homomorphisms from a semi-group into an abelian group,
Right.
which means that you actually don't lose anything if you already enrich that semi-group and you formally add inverses, because he was only interested in abelian group values invariant, abelian group valued invariants, homomorphisms whose target is a group. And in that reason, there is no reason to go beyond semirings, but I'm just about to advertise that you lose a lot. You lose a lot by not going, by not staying within semirings, I'm sorry.
Right, so, I mean, tensor with Z, that's a way of...
Yeah, you can do that.
So, Grothendieck didn't really have to go to groups. He could have stayed in...
Correct, but he would not have exploited, I think, anything that is special to semigroups, even if he only stuck to semigroups, because he was only interested in group valued invariants, homomorphisms from a semigroup to a group, so those all factor through the Grothendieck group. So like the difference is invisible.
He was interested in this for homological algebra reasons? Or?
That kind of thing. Ultimately, it's a replacement for cohomology, except it comes via different construction. So this K theory was the first example of what was called an extraordinary cohomology theory, no longer called extraordinary because people, with 50 years hindsight think that it's a pretty ordinary thing to do. But in 1960 it was extraordinary, and that was one of the big families. The other big family was Bordism, but they were always abelian group valued. I don't have, by the way, a historical explanation at all. I don't know how Grothendieck chose his definition, or whether he had any kind of foresight, but I think he wouldn't have exploited the kind of combinatorial restriction of a semigroup, even if he made that definition.
So, to understand the definition a bit, okay, I get SKFC, right? That makes sense. Right?
Yeah.
Where you've defined these isomorphism classes and you've got set theoretic operations and you're semiring operations.
Mm-hmm.
So what is KFC? So what is, is to be a group, what's negation in it? And
it's got to be formally added.
okay.
So that you have a generator for the additive inverses, right, if you like.
And then you only have
like
multiplication and not addition, right? So
no, I mean you have addition, and the multiplication is consistent with that formally added
Quotient is
inverses.
down by all relations.
but I mean, if it's an abelian group, you only have the group operation, right?
No, the tensor operations, I mean the product operation still survives and formally extends to it.
Okay.
I'll give you just a better way of looking at it.
Okay, thank you, that's what I was missing.
I'm sorry, then I missed what I should have said. What is it that I should have
Well,
said?
additive abelian group.
Yeah.
Makes it.
Yes.
Yeah, I just...
Oh, multiplication has no inverse. Yeah, it's just an additive.
That's okay.
Sorry, okay, yeah, that's the answer. All right, and because the Bernstein legal of finite G sets is a nice example. And this is what a semiring is, as usual. Let me just give you my favorite examples of semirings that I learned from Schanuel. Oh, by the way, no, this is a question I wanted to ask you guys. Not from me, but from the master himself.
No, you gotta read it.
I need to read it, you said?
Yeah.
So characterize the semirings that are isomorphic to the Grothendieck semiring of some small distributive category. So if you have a small distributive category, there's an associated semiring. And which semirings arise this way? Turns out that these are special. These are very far from arbitrary. The semirings, which are these not fundamental groups, but isomorphism classes of objects, blah, blah, blah. So what are some characteristic properties of these semirings? Schanuel lists 5 of them, and some of them are equational. It tells you that 1 is special, that 0 is special, these kinds of things. But then Schanuel also lists something which is basically a consequence of pullback, which has this kind of shadow or implication on the Grothendieck semiring of the category, which makes it very hard to exploit, I think, and if I give you a semiring, for you to answer the question, hey, is this the Grothendieck semiring of some distributive category? Let me just tell you what this particular observation is.
What was the word you used? Shadow or?
Shadow.
Or then you used another word. Implication?
Shadow of implication.
You read
Oh, shadow of implication. Okay, fine. Sorry.
You have to rewind.
No, let's
Promise
go.
me not to publish this.
No, let's go to the videotape. No, I'm just kidding. Go.
If you have a sum of things that are equal to a sum of things in your semiring, then there exists a matrix such that the columns of this matrix add up to the A sub I, A sub 1, A sub 2, A sub 3, all the way up to A sub n. The rows of the matrix add up to the B sub J, B sub 1, B sub 2, B sub 3, all the way up to B sub n. And this is the Cij in there. So if you have this consistency that the sum of the columns is the same thing as the sum of the rows, then there are entries in here coming from your semigroup such that the column rows and the row rows are as prescribed, once again subject to the consistency condition. So where do you fish out these entries? I think it's because you have pullbacks. So you have a sum n included in this big sum, and you have a sum n included in this big sum as objects, you form the pullback, and then this isomorphism type is represented by an element of your semiring, so you can do this. So this doesn't come from nowhere. Not every single semiring is like that. Every single ring is like that. If you have additive inverses, you can just choose if you want to this block of the matrix and you just plug in these holes such that the row columns, such that the row sums are as prescribed, and you plug in these such that the column sums are as prescribed, and then this is consistently again determined. So this is, as I say, a shadow of the fact that there is something like a kind of, you know, a pullback is a little bit like a subtraction, not quite. But so, you know, this extra structure of your distributive category puts a restriction on what the Grothendieck semiring can be. But this is not an equation or condition. This just tells you that these CIs exist, and even though they are here constructed kind of functorially, let me remind you that the representatives of the isomorphism classes are not canonical. So it's not even sure whether you can choose this functional or functorial or whatever. And you know, on the nose of it, this is an existential condition, not an equation. So how do you exploit this? How do you characterize the semirings that satisfy just this thing? And how you make use of it, if you have it, to construct, you know, a categorification of it, meaning that you are given the semiring and you want to construct a category whose Grothendieck semiring it is. I don't know. But I think this is a question in a new direction. So people are able to categorify a number of constructions coming from cardinality to begin with, and then division, multiplication, and everything. Try to categorify a semiring, and I think this is a great challenge. So, my second favorite semiring is the natural numbers, as usual. My favorite semiring is this very strange thing. I had no idea what to make of it until I started reading Schanuel's article. So here, the multiplication operation, first of all, we have to adjoin something, like formally add, not adjoin, but formally add another element that's infinitely small. This turns out to be the additive inverse. Sorry, the additive zero, additive identity. The times operation is the natural number sum, and because we have added something that's infinitely negative, once again that behaves under multiplication like a zero.
Yeah, the bottom.
And then this is the addition of this semiring, and that's the max operation. And then if you max something with the infinitely small thing, then that is that thing. Nothing is more than the infinitely small.
So that's the tropical semiring.
Yeah.
That is the tropical semiring, except not for the reals, but for natural numbers. It's exactly that thing. And yep. So something that I love and did not know is that this is finitely presentable. So a finite presentation of not the tropical semiring over the reals, but this tropical semiring over the natural numbers is that you need to add these two equational conditions, because there are no inverses. It just has, you know, that a word equals another word, not that something is equal to zero. And it just kind of, you know, playing with symbols, exactly of the type that you always hated in high school, like there's no shortcut, to justify that these two generating relations are enough and just the right thing to quotient the polynomial ring, the polynomial semiring, so that you get this tropical semiring. And here's an explicit isomorphism. So the infinitely small thing is the zero on this side, and the natural number n is the formal variable raised to the nth power. Or you can recast this thing yet again, this is also in Schanuel's, by saying that you have a multiplicative symbol that generates the natural numbers. This is not zero, this is the infinitely small number, this is q to the minus infinity, this is q to the 0th power, this is q to the first power, and then what used to be the sum operation, here it actually is multiplication of these symbols, meaning summing the indices, and the sum operation is taking the bigger of two symbols, and you declare that q is greater than 1, and so greater power of q is greater than the previous one. Just another way of looking at a very simple semiring. But you know, I grew an additional, how may I say, depth of admiration for semirings after this example, and what it means to present a semiring by generators and relations. It is really word problems. Like it's a lot of hand calculations.
Classical. 1 minute.
Go back?
I was wondering if there was a way to think of that in terms of binary digits. I'm not quite sure.
There isn't so much room for binary digits, I think, because it's just the natural numbers and something that's infinitely below the natural numbers. It's really one-dimensional, like, you know, just linearly ordered.
I mean, I think it like embeds into like kind of an idea of like orders of infinity.
Okay.
Why do
Oh, you mean orders, like, you know, growth orders.
Yeah.
Like it
Yeah.
grows like x to the n. So this
Yeah.
is like, you know, function whose asymptotic growth is x to the n, and then the product of two functions versus just dominance of the functions. Those are the two.
Or I just think
operations.
of it as a discrete version of your Iconal construction that gives your usual tropical thing.
Yeah,
Yeah.
that's it, absolutely. Once again, the fact that it's finitely presented actually plays a role at some point.
Okay.
Okay, so you also in this adjunction, this is one way of answering your question about how you get from a semiring to a ring. It is just a formal free process of adding additive inverses, and it's compatible with the multiplication. And this is what Grothendieck did by hand, you know, when he defined the K-groups. He actually wanted for those vector bundles some operations to have formal inverses, so that they behave the right way. For example, when you write down formulas for Chern classes and these kinds of things, these Chern classes are valued in a ring that's kind of, you know, graded, commutative, and it's just nice to have formal inverses sometimes. This is the same thing as stabilizing vector bundles in the geometric setting. So it actually came to him very naturally to add this process.
Yeah.
To add this equivalence relation of stabilization to just vector bundles. And that gives rise to the K-groups as opposed to just one half of the K-groups. All right, so the semi-ring, sorry, the ring associated to this semi-ring is just usual Fendor integers. And then the ring associated to this tropical semi-ring, if you think about it, so if you have two elements and you add the same thing to them and they become the same, then they were the same to begin with.
Yeah.
This is what happens on the side of the Grothendieck ring. But then here, if you have any two elements, you can find somebody above them. And so that means that you add to them and they become the same. So the associated Grothendieck ring is just a trivial ring. And this tells you this kind of dichotomy that comes up later on, I guess, in Schanuel's article as well, that the kind of rings, this is like dimension. The way that it behaves is just like dimension of a simplicial complex of a topological space or whatever. So the kind of semirings that behave like dimension, they are the exact opposites of the semirings, which are good targets for the order characteristic. This is a kind of moral that comes out later on, that is my understanding of the story.
So you really lose information. You really lose information.
Here you lose everything. You lose as much as you can, totally. This is very far from being part of a ring, and this is very close to being part of a ring.
Here,
That has a very like large kernel to it.
Yeah. This operation squashes like, you know, one half of the mathematical universe into nothing, and that's the interesting half, and to some people anyway. So it's the lack of cancellativity. So here we have cancellativity, and you have an embedding here, and then here is just the very opposite of cancellativity, and so everything goes away.
Can you go back a bit? Sorry, you
Apologies. So the Grothendieck ring depends on the Grothendieck semiring functorially. So you can't possibly lose information by focusing on the Grothendieck semiring. However, you do and often can lose information by focusing on this side and not on that side. Okay, so forget about this slide here, it's not so essential, but because I try to advertise some of these things to logicians sometimes, and the term definable comes up all the time. To them, it means something else than to other people, and I belong to the other people. And this is just one way to make concrete what it means to talk about definable subsets of Euclidean space, or definable subsets of the powers of some set. So the term, you know, definable using some kind of algebraic operations and inequalities comes up very soon. And this may seem like a very unnatural way of introducing this story, but somehow the definable is the following. definable by a first-order logical formula, so you do allow quantifiers as well. This is the hidden intuition behind this definition. If something is definable, then all the Boolean operations that you involve are not going to lead outside the domain of definable sets. This is just like quantification. So you say that there is something, so projection is just like, this is going back to over here, and you know, everybody else, that projection is just quantification, if you like. And you get both quantifiers because you have negation. And then you have to be able to talk about individual singletons. So let's say that every single singleton is definable. And you have to be able to talk about equal as a relation. Relations are represented by their graphs. And so the notion of equality of n tuples is represented by the diagonal of this Cartesian power. And this is one of my favorite books of all time, really, of all of mathematics, and almost all of my knowledge of all minimal structures, whatever they are, come from this very lovely little book, written by a model theorist, but with a very geometric bent. This is one way of talking about logic and first-order definable sets that doesn't mention either logic or first-order. It does mention definable, but it's just a nickname. If you have a bunch of sets like that, definable sets, you can associate a category to that. The objects are definable blobs. And what is a morphism between two definable blobs? It is just a set-theoretic function whose graph itself is definable, and that graph lives in one of these Cartesian powers. And so you can talk about the category of first-order definable subsets of Euclidean space using some specific first-order signature. Or you can have the syntactic analog of that, and you've all seen this, you know, zillions of times. And if you have a theory in whatever logic where this actually makes sense, you can associate a syntactic category to it. And this too goes by the name of definable, except it's not kind of definable subsets, but just the formulas defining them and the definable morphisms between them. And this is then something whose homomorphic images can be thought of as a definable sets in the model and so on. But this is another good category to play with if you're interested in distributive categories. So if you have this model theoretic geometry, then the associated category of definable sets and objects is very nice. Other than quotients, other than co-limits, it behaves just like sets. On the limit side, it's almost exactly like sets. It's Boolean because we are all very classical in our thinking here. And if you have full first-order logic here, then the syntactic category shares these properties at least. Not if you restrict yourself to just a coherent fragment, and not if you restrict yourself to intuitionistic logic, but in the first-order setting, it is just as neat. So these are the sorts of categories which are the distributive categories whose Grothendieck ring Schanuel works to understand. Look, it may not be just very kind of evident from this definition how picturesque and easy it is. So I like to make it like, you know, picturesque and easy. And if you don't mind, then I'm going to doodle over there, hopefully outside the view of the camera. Like, how do we think of the category semi-linear definable sets and semi-linear definable morphisms over the reals? Or how I think of it anyway. So to define something means that you separate a bunch of points, a subset of Euclidean space, using the operations of sum, using the operations of scalar product. You are allowed to compare two things, and you are allowed to name the reals. Like you can use pi and you refer to it. This is actually a big deal because you are not always allowed to use constants in this first-order logical setting. What is it that you can do? You can basically say that a bunch of variables multiplied by some coefficients is less than 0, or less than equal than 0, or equal than 0. And you're allowed to take Boolean combinations of these inequalities. So this is Boolean combination of linear inequalities. What is it that you can create out of Boolean combination of linear inequalities? I know the object, the typical object, may be something like, I know, this is a cube And then there's a little triangle that's kind of, already another square that's kind of, sticking out in space. This is just a three-dimensional example, so it's all happening inside R3. And there's this infinite ray that's shooting out, but then you kind of omitted a point there, and you maybe omitted a line segment there. But it's like, piecewise linear structure. It's a Boolean combination of piecewise linear definable things. And geometrically, it would be very, very odd. And then here's another object that I know, once again, just see the example, something like a pyramid, and there's this hollow kind of opening inside, and then just see it's got a little antenna. What is a function between these two? It is a set-theoretic function whose graph in the appropriate, six-dimensional space is piecewise linear in this sense. So what does that mean? It means that you carved out this thing into smaller piecewise linear segments, and you apply the linear function to it, and it landed inside that object. So like, piecewise linear map, piecewise linear map, not necessarily continuous.
It sounds like something linear. Why is it called semi-linear?
Because of the less than.
Piecewise.
Because you're allowed to say this.
What does that
In
mean?
linear algebra, in your linear algebra courses, do you ever use less than?
No.
And chances are you don't, right? Linear algebra is in fields, right? And they need not be ordered. So here the semi thing actually comes from the fact that there's a positive part of things and there's a negative part of things. If you like, there's a comparison, there's a less than, and that's part of the language. And so you're allowed to cut out a half ray, and you are allowed to cut out an interval, you have to cut out a cube and what have you. So, but the fact that it's not continuous to a topologist, this is a big price to pay, because we love continuous maps. But then here the underlying intuition is that as long as it's definable in this first order vocabulary, it's allowed. And so it's not completely arbitrary because you can only divide into finitely many chunks. So infinite subdivisions are not allowed, that will be not first order logically expressible. So that is a little kind of remainder or relic of continuity, that it's finitely many pieces. All right, what is a semi-algebraically definable sets and morphisms over the reals? It's not much worse, except you allow polynomials. So semi-algebraic. So here, you are allowed to use multiplication, including your formal variables and what have you, and also constants, summation. You can, because it's first order, you can talk about inverses, you can talk about negatives, and you're allowed to compare two things once again. So the kind of shapes that you can carve out using a first order formula in this signature is just like this, except it's a bit more curved, like it's part of a paraboloid. And then you cut it into it with a certain plane, and there's also a ray coming out, and all kinds of algebraic curves. It's the same thing except involving higher order polynomials. And once again, the other object may be something curved like that. And then the map between them is something that's piecewise algebraic, but no longer piecewise linear. Not necessarily linear. So piecewise algebraic maps. Certainly not continuous either. All right, so this is a, sorry. Yes?
But I guess a map that might, does there exist in this like a map from the line to the circle?
Here?
Yeah.
Yeah, you can do that. Absolutely. Does it bother you? It's okay, yeah. Absolutely, yeah.
I'm just wondering how you do that.
Well, it's point piecewise.
Listen. Rational functions are okay. This is a rational function. It's okay. Projection is a rational function, and you can express rational functions as well in first order logic. So you are allowed to wrap a line around a circle, missing one point. Is that what you have in mind?
Yeah, I see how that works. Okay.
All kinds of projections between the plane and other surfaces, they are algebraic.
Well, you also said point piecewise, I could chop the line in half, wrap one half around the bottom, one half around the top.
It's got...
It's just,
It's got
It's
quite
just
a
the
bit of...
wrapping that was possibly the problem because you don't have trigonometric functions.
Oh, I see what you
no,
mean.
obviously.
Yeah.
Oh, wait a second, wait a second.
Oh, it
Sine
doesn't
and,
matter.
just a sec, sine and cosine don't live here.
No.
The graph of sine, no.
Yeah.
The graph of cosine, no. This kind of parametrization of the circle that you do in calculus,
No.
that doesn't belong here.
Right.
However, this parametrization by rational functions, which happens to be bijective outside the single point, that can be done using rational functions. So that's a particular way of parameterizing a conic section by a line, P1 if you like. So, you know, point sets theoretically you are allowed to cover it, but not in the sense of, you know, arc length. Arc length, a lot of transcendental functions have no role to play here, and if you throw them in, then you lose a lot of goodness.
Right.
And then if you just think of an abstract field, like, you know, even for the complex numbers, right, you don't really have, you know, less than, and if you think of a finite field or algebraic closure of a finite field, you can still keep these two elements of the algebra in the signature, and you can refer to elements of the ground field, but you are restricted to polynomial expressions and Boolean combinations of polynomials, so that's no longer semi-algebraic, those are called constructible, and if you want to, then you can look at all kinds of subcategories, bounded, and that's an especially good one that's going to show up in just a second. All right, so wait a second, what are we trying to do? Give me the Grothendieck semiring of this category. And convince yourself that the Grothendieck semiring of this category has a finite representation. It's a finite representable semiring, and the same for this gadget, which seems to be, which is like, you know, uncountably many objects and blah blah blah. But it all becomes very natural, I think, in Steve's presentation. So nobody is allowed to leave until you convince me that this is not trivial. We are in this world, so maps are piecewise linear. This is the closed unit Q. It turns out to be important that the boundary is also included, so it's the closed unit Q. And this is your favorite pyramid. Let's see a regular tetrahedron. And I want a point-for-point bijection, so it's an isomorphism, which is of this type, it's piecewise linear.
Right. But it does not have to be continuous.
Doesn't have to be continuous.
Ah.
You are allowed to kind of, you know, divide up this solid cube into finitely many chunks. On each of them, you have to use a particular linear map in the standard sense, linear map, in such a way that altogether they establish a point-for-point bijection between these two geometric fields.
So a dissection problem.
This kind of dissection problem, let me try to convince you that one of the reasons this is not trivial is that we want to have a point-for-point bijection. You've all seen this in high school, I think, and it goes back to Euclid, no doubt, like, you know, and then you do this, and you do this, and you fold this up, and wow, the triangle becomes a rectangle of the same area, incidentally. It doesn't matter that they are the same in this case. I want to say this is cheating. And the reason it's cheating is the following. Think about these points.
Well,
Just a sec. After the folding, where do these points go? So these points, they belong to, say, the bottom segment here, and then you fold up the top, and you're actually going to miss these points. On this side, you are going to miss these points literally. These points you are going to get. These points you are going to miss. And so what you have is a point for, and you know, don't even think about those points, like what exactly happens to them. Some of them end up on this side, some of them you're missing from here. And then this point in the center, you know, that's counted 2 or 3 times, but you can only count it once. What you have really established is not a point-for-point bijection between the closed triangle and the closed rectangle, but between the closed triangle and something that has, like, you know, missing points and all kinds of annoying little places missing. And look, it's piecewise linear and
But
everything.
you also have double.
and double.
And you have double points, all the much worse, right? So, like, you know, convince yourself that you can actually do this. Okay, you don't have to restrict yourself to 2-dimensional pieces, of course.
Sure.
But you can establish a point-for-point bijection between the closed triangle and the closed, of any area, by the way, of the closed rectangle, and then try to do it in 3 dimensions. So, this is something that's actually needed for the proof. Sorry?
Get rid of a lot of, it's obvious how to get rid of a certain amount of those missing points.
I mean,
Well, instead of flipping
Like, I can come up with a pretty easy one, right? Like, we just take all, like, we take the first triangle, we cut it off, and then we pull all of the borders off, reassemble the shape, and we'll have, you know, an open rectangle with some slices missed out of it. I can just take pieces of what I cut off before and fill it back in.
Indeed, we can now go home nearly. I think you have to convince yourself that this thing and say this thing are equidecomposable. And there's still a little bit of an issue, because if you, like, you know, this T-shaped thing is missing, right?
Yeah.
So that the T-shaped thing and part of the boundary is equidecomposable, and then you may be left with leftover points, and then you have to worry that in the end you have, like, you know, 5 extra points here that don't go nowhere.
Yeah, you have to.
It actually needs a tiny bit of thought, and this is going to come up later, that down to the level of points, including the isolated points, they are going to travel to the right location. However, I need to thank you, you can go home. This is the answer. Yes, you can do it using skeletal arguments of this type. And don't try to do it using rigid motions, of course you can't, even if you double point, even if you double count, you know, the two-dimensional or one-dimensional segments. You have to use some affine distortion. Here you go. So this is the reason that I am here. And maybe this is the reason that you are here, I'm not sure. You can contradict me and you just say that I should shut up. So to me, this is the least obvious statement, you know, so far that I've encountered. And then once you think about it, it becomes very, very natural. And so this is the beauty of this particular exposition. Yes, this is the final presentation, a single generator and a single relation. It's a countable semiring. And that's the Grothendieck semiring of this thing.
Wow.
It turns out that, you know, for some very strange reason that maybe I'll get to later, the Grothendieck semiring of this animal is a simpler one than the Grothendieck semiring of this animal. Schanuel also computed this one. So let me try to walk you, well, the steps involved in this process. And once again, this is an exposition of 2.5 paragraphs of Steve's.
One second, are you going to do the semi-linear also? Are you going to say what it is?
Yes.
Oh, okay, fine.
Extracting what I think are the steps of the argument. So the first one is, first of all, with hindsight, it turns out that this is a geometric statement of a type that you've all seen and understood. It is just wrapped up in this mystical looking relation. But the fact that this single mystical looking relation is responsible for all the reassemblies that can go on, that is still something that's not trivial. So here are the steps of Steve's proof. Like I say, algebraic games with semirings. This is a specific semiring, just an abstract piece of algebra. That's our old friend, another abstract semiring. This is a particular homomorphism that you can construct by hand. You just actually have to say what the generator does, and it respects the relations, and there you have it. It's a homomorphism. Okay, there is another homomorphism from this kind of mystical looking semiring rather, into the integers. Let me just call it, this is actually the Grothendieck ring associated to this ring. So a bit of calculation tells you that this is the ringification of this semiring, and this is the embedding of this semiring into the associated ring. You don't need to know it because you can establish that there is such a homomorphism just by saying that the generator goes to -1 and that the generator satisfies this relation, and then that is a homomorphism. Yes?
So an example of things that you could use to represent this ring are 1 as a point and x as an open line segment.
Something like that. You have no choice about 1, that has to be the point. You have a certain amount of choices about the generator x geometrically. And then you have it. You just by eyeballing it, you realize that this is the answer. You did not read Schanuel's article already?
I did not read Schanuel's article already. Like 10 years ago, I read like John Baez's like This Week's Finds.
There you have it. I don't think that John discovered it all by himself. I think it goes back to the source, and I think the source is still Schanuel's
yeah, I mean, he said that he read this, but at the time I couldn't find the original paper online. So.
Maybe this is not original with Steve either, but I think it's worthwhile seeing the steps anyway. So you have it. Sorry.
Never mind. I was saying that there's like a tree interpretation of this x equals 2x plus 1.
Is that right? I've never seen the tree.
It looks like that's 7 in 1 paper, anyway.
The 71 paper, I don't think that involves this semiring.
No, it wasn't, but it was what, anyway. I could be wrong, I'm just saying. The
I'm-
relation
I'm-
looks like a tree thing.
I'm in the way of constructing a diagram that's not so very big, and it's going to come up on the slides in just a sec. But maybe it's better if I construct it here live.
Yeah. Plus,
Yeah, yeah.
plus a root.
Yeah, so it's not a,
Is it?
Well, you take a binary tree,
Yeah.
take out the
Oh, I
root,
see
get
what
two
you mean.
binary
The
trees.
self-similarity of the binary tree is the same relation.
yeah.
Yeah, you're right. Okay, maybe,
I don't
maybe.
know what to do with that, but that's why I said it.
I see. I'm not sure how to tie that in
So
here.
think of X as an infinite binary tree.
I know the self-similarity of the binary tree is exactly like that. I don't know how to tie that in here, because it's got to be an infinite tree for it really to be translatable that way. And then this is all semi-algebraic, so this is like, it doesn't allow infinite branching. So the infinite tree literally is not an animal in here. It doesn't allow infinite branching.
Sure.
The diagram that's about to emerge is the following. We have this mystical looking ring, and so that's the polynomially modularly single relation. Oh, and there's the homomorphism from here into the dimension ring. This is just like the dimension of an algebraic set across Z, which is just like the order characteristic of this algebraic set. And whatever pieces of notation I chose for that, so this is the first one I called SCH, or this is the same thing as dimension once this turns into geometry. And this second one is the Grothendieck homomorphism. Same thing as the order characteristic once this turns into geometry. It hasn't yet. This is all playing with symbols and relations. So, on the right-hand side, we have the Grothendieck semiring of this animal. Very abstract looking, but very concrete at the same time. On the left-hand side, the purely combinatorially defined semiring. What it means to give a homomorphism of this type is actually very, very simple, because if you know where the generator goes on the other side, and the generator satisfies this relation, there you have it. And that's the only thing that's needed. So what is the generator X? Where does the generator go? As you've indicated, it's got to be an open and got to be finite is probably better line segment. If you want to, it could be like piece of a parabola, but this is the best thing to do. What does it even mean? By the, it means the isomorphism class of this thing, right? In Grothendieck semiring. So what does it mean that 2x plus 1 is equivalent or isomorphic or whatever to x? It means that you can do this. If you have an open finite line segment, then you are allowed to remove a point in the center, and this is isomorphic to that. This is also isomorphic to that. So both of them are in the Grothendieck ring, the same animal. And remember that even though this is discontinuous, you are allowed to move the pieces away. It's piecewise linear. So this thing actually is the same thing as line segment, the open interval, point, and another open interval. So this is coproduct. So this is plus. And so on one side you have x, on the other side you have x plus 1 plus x. This is it. So the fact that the ground is ordered, meaning the ground field is ordered, is the reals, and that it's kind of two-sided and there's a point or whatever. Okay, so this is enough to define this kind of thing. But wait a second, if you think about this homomorphism literally, what is the kind of object that you can build up inside semi-algebraic sets? So this is a semi-group, semi-ring homomorphism. So x goes into this interval. Where does x to the n go? Well, into a cube. And then where do coproducts, meaning pluses, go? I'm sorry, just pluses, not coproduct, but just pluses. They go into coproducts. So on the other side, you have open cubes, finitely many open cubes of various dimension, kind of finite collection of these. This is the isomorphism type here that you are going to hit. And you have to know that this is actually all the isomorphism types there is. So that this is surjective. It turns out to be much more than surjective later on, but for the time being, we just need that this is surjective. So what does it mean? You have a complicated semi-algebraic animal, but you can chunk it up into open cubes. I'm sorry, something that's semi-algebraically isomorphic to open cube, and a bunch of open squares, and a bunch of open line segments, and a bunch of points. So that the isomorphism classes that are represented in the Grothendieck semiring are actually hit by the image of this morphism. And this is geometry, and this is very tough. And you have this very crazy collection. It's defined implicitly by implicit polynomial equations. You want to know that you can triangulate it, and then you want to know that you can turn the triangles and the simplices into cubes.
Oh.
Turning the simplices into cubes is no biggie. Triangulating this kind of thing is a Hironaka's theorem. It was worth almost, Field's medal. I mean, he did much more. He actually did resolution of singularities. And just as a side, when he showed the semi-algebraic triangulability of semi-algebraic sets. But it's a very deep thing that you can do it using finitely many triangles, meaning simplices, and then later on you turn them into cubes, and you get that this is 1, 2. So there's an arrow missing here, and you put in the arrow, and you show that the diagram is commutative, and there you have it. Because once you know that this is a commutative diagram, and this is mono. I forgot to say that this is mono. I think I did say that that is mono. You need the fact that that is mono. Here you go. This map is injective. Once you have a diagram of this type, it's commutative. This is mono.
So then the factorization, and then you get it's identical.
This is mono, and so this is iso.
Nice.
So this is why it's enough to show that this is onto, and this is a hard geometric side. It's enough to show that this is into, and there's the algebraic side. And you need to know that you can complete the diagram, and from this Grothendieck semiring, you can hit the same targets. And so this is what I advertise as the map that associates to a semi-algebraic set its dimension, and the empty set has dimension minus infinity. Minus infinity is less than all the natural numbers. You need that if you want to complete this to a semi-ring homomorphism. And then the other is the Euler characteristic. The Euler characteristic of a semi-algebraic set. First of all, it's invariant under this kind of garbage. So it's actually not just going from semi-algebraic sets, but from the Grothendieck semiring of semi-algebraic sets. So that's kind of quite a step. And then you have to show that this commutes, which is then easy, because you only have one thing to check, that the right thing happens to the open interval.
Sure.
But then, let me just remind you how the dimension and the Euler characteristic are defined. So this is one way of thinking. You don't need any deep definition of dimension, but just say that if it's got something that locally looks like a piece of n-dimensional space, then the whole thing, which can have different dimensional components, you just pick the highest dimensional component, and that's the dimension of the whole thing. And under disjoint union and under Cartesian product, it behaves like these numbers do. And so this is why this is a semiring homomorphism. You do need the fact that the nothing goes to the nothing there. How about the Euler characteristic? Again, it comes, if you like, from triangulations.
Clock now. Just
You have a semi-algebraic set, and you triangulate it into open simplices, and you add the alternating sum of the simplices. So one-dimensional simplex, meaning the point, comes with a plus sign. The one-dimensional open interval comes with a minus sign, and so on. This alternating sum on the right-hand side doesn't depend on the actual decomposition. It's a well-defined combinatorial invariant, and under disjoint union and under product, it behaves the expected way and gives you another semi-ring homomorphism. So, like I say, I come from algebraic topology ultimately, and so one very, very annoying thing about this combinatorial Euler characteristic is the lack of a very tight relation to Betti numbers. And you know that the alternating sum of the number of cells is the same thing as the alternating sum of the Betti numbers, except not in all cases, it's only when they are defined and everything. So I'm not sure whether I should be doing it because no song you have to do, right?
No, don't worry about me. You're doing beautiful jobs.
So
You do your thing.
if you don't mind these cartoons that I'm sketching here on the blackboard, I don't know, you could have something like open, I don't know, open square. And you could have something like the closed square. I'm sorry, by closed I mean that all the boundary components are also included, and then here it's open, so the boundary is not included. Closed square. And you can have something which includes part of the boundary but not all of it. For example, include these open parts of just those two sides, you know, partly open, partly closed, and here's something. Open square, and I include the corner. Plus one corner. Open square plus two open sides. All right, so this one is compact. As a topological space, it's compact. Oops. These first three are locally compact. And this animal is not locally compact. I'll show you in just a sec what it means to be locally compact. Alright, think of this point, and think of any neighborhood of this point. By neighborhood, I mean closed neighborhood. So closed neighborhood means basically the intersection of this thing and a small closed disk in the plane. And that intersection is not compact. Never. So you cannot find a neighborhood of this point that's compact. Here, if you pick a point here at the boundary, and you intersect it with a little closed disk, small enough, then you do get a compact set as the intersection. And here as well, because you cannot be at the boundary, you cannot be at the corner, you can always find little compact neighborhoods at any point. And this is just compact on the rules, and open is okay. For locally compact spaces and for compact spaces, suitably define the alternating sum of the Betti numbers is the same because the alternating number of the cells. But for spaces that are not locally compact, I don't know a cohomological, meaning Betti number type interpretation of the alternating sum of the number of cells. So what is the alternating sum of the number of cells? 1, 0 cell, and 1 being 2 cell. So it's 1 plus 1. So the combinatory of Euler characteristic here is 2. Here the combinatory Euler characteristic is you have 2 minus 1s, and you have a single plus 1 coming from the square, the open square, and no extra points. So the combinatory Euler characteristic is going to be minus 1. Here the combinatory Euler characteristic is 4 points, 4 open intervals, and 1 open square, and you add it up to the right thing, 4 minus 4 plus 1, so that's going to be 1. It turns out that these numbers are not replicated by the Betti numbers, but the alternating sum of the Betti numbers spits out the right invariant, and then here I don't know anything with that. So why is this kind of important? To a topologist or to an algebraic topologist, these spaces are big and stupid and wasteful, because this is contractible. This is actually contractible to a point, and so the Euler characteristic should be the same thing as the Euler characteristic of a point, and it really is. Well, this thing is also contractible, even though it's only locally compact, you can do something like this. Also for here, you can sort of shrink this to a space to something that's clear, not two-dimensional anymore. You can really simplify these calculations. But then here, I don't know anything to get at the combinatorial Euler characteristic except to triangulate the space, basically. And you want to think of a triangulation of a space as usually wasteful, even for very small dimensions, if you want to do it computationally. Like this massively exponential number of simplices that you add up to arrive at a small integer as the answer. It'd be nice to have homotopy invariance here. And so I guess I just mentioned this on the next few slides as an advertisement for algebraic topology, in case it needs it.
I guess anything that, is it true that anything that bounds adds up to like any boundary of a closed subspace is
Yeah, I
going
think
to be
so.
0?
You must be able to do something like that. So where does that really come from, that kind of relationship? Maybe a shadow of Alexander duality or Spanier duality or something like that. But I need to think about it. I mean, that simplification is rarely applicable, right? I mean, most of the things that you look at are not the boundary of something. If you are so lucky that you know ahead of time is the boundary of something, then there may be some simplification
Well,
involved.
there's one nice case where it comes up a lot, which is closed cubes and open cubes being the same.
That too, yeah, you can do that. But once again, if you have a random looking collection of these simplices, you are typically not so obvious to say right away what's happening. I don't know the answer to these questions. So is the combinatorial characteristic the same thing as the alternating sum of the compactly supported Bethe numbers for all semi-algebraic X's? And to be a proper homotopy invariant means that the homotopy by which you deform the space has the property that the preimage of a compact set is compact during this homotopical deformation process. And compactly supported Bethe numbers are invariant under proper homotopy. And so this order characteristic is also.
Doing homotopy, would you also do some, I guess, problems, like, restrict to homotopies that are, semi-algebraic?
You can do that under semi-algebraic
Assuming that they are
homotopy.
the continuous ones.
Under semi-algebraic continuous homotopy, they are invariant.
Okay.
But you may not have the luxury that you know ahead of time that it's a semi-algebraic continuous homotopy. So you are maybe sometimes lazy and you just say that it's topologically fine. You want to use sine and cosine on a circle or something like that, so it's not semi-algebraic. So it's actually nice to be able to say something in the topological context. This is not much to say, by the way, that it's topologically invariant, but it is topologically invariant. And this is again something that goes back way, way, way to Milnor, that topological homeomorphism and semi-algebraic homeomorphism do not coincide even for semi-algebraic objects. So to say that something is invariant under topological homeomorphism allows the kind of infinitary approximations and kind of limit processes that are impossible for algebraic maps.
So now with this, is there some invariant one? Because I'm thinking of the regular Haber-Mutter, I don't know what variant to use, what kind of invariant did he use here to show that?
Milnor? He used oh darn, it's at some point it's going to come back to me, but it's a pretty classical invariant having to do with the actual combinatories of simplices that keeps the dimension of the simplices. So you are not allowed to decrease the dimension of the simplices. It really is about an actual triangulation. And whatever twist or whatever it's called, at some point I will remember it. This is the invariant that lets you distinguish length spaces, that the length space 7, 2 is not homeomorphic to the length space 7, 1, even though they have the same everything. I apologize that it doesn't come back to me, but it's something that was discovered before Milnor, like a decade before Milnor, and he used that to show that they are not simplically homeomorphic, even though they are homeomorphic by, again, an explicit homeomorphism that he gave. Alright, so what else is there to say? Yeah, this is the diagram, you've all seen it. Oh yeah, so this is another way of saying how variable these two invariants are. One is just the dimension, the naive topological dimension, and the other is this combinatorial defined order characteristic. If you know these two invariants of two semi-algebraic sets, and they are the same numerically, then they are the semi-algebraic sets are semi-algebraically decomposable. So these two scalars actually determine everything that is up to isomorphism in this category. In other words, the isomorphism types in this category, there are very few, they are parameterized by two integers. They are not completely arbitrary, but nearly arbitrary. That doesn't tell you how the algebraic operations of co-product and product behave. When you also put that in, then you get the full description of the Grothendieck semiring. So I don't know if people want to see the way that this is done. This is another way of saying, by the way, here, topological dimension 3, topological dimension 3, combinatorial order characteristic 1, combinatorial order characteristic 1. So these two must be equidecomposable, in fact semi-linearly, but semi-algebraically certainly. So this is a particular answer to this puzzle.
All those three solids that argument works for, right?
In fact, for any kind of solid body which has a single three-dimensional component, and whose Euler characteristic, combinatorial Euler characteristic is 1, it's going to be semi-linearly equidecomposable with this paradigm if you want to, or that paradigm or whatever. So do people want to see how to do it, or do they not? By the way, you have the answer in some sense. I just wanted to convince you that it comes courtesy of this single relation that I erase. This single relation and the multiplicativity and so on, that is enough to show this. If I do tell you this, then you can really go home because I mean it's been like overdrive and overtime. I can show you where this is going, and you can invite me like for next year.
Next semester, yeah.
That's next year too. Maybe. Well, next.
Well, I thought you were going to state the semi-linear relation, unless I missed it. Did I miss that?
Well, if this is a semi-arch,
Right.
then they are semi-algebraically. This turns out to be true in the semi-linear world if they are bounded.
Okay.
Something that is not true in the semi-linear world is the following. The open line segment and the open ray, they are not isomorphic.
Okay.
If you are just restricted to piecewise linear functions, you can't stretch this to be infinitely long. So that these two are actually distinct, are not isomorphic. And this actually makes the Grothendieck semiring of this thing complicated, more complicated than the Grothendieck semiring of this thing. And the recognition principle is harder here. So I was a little bit cheating. The fact that these two are bounded, that's actually a bit of a help. So here's the peeling idea of peeling away the top dimensional simplices, that works beautifully. So if you have points, then you have to have the same number of points. You have to know that you can decompose your objects into a disjoint union. Now this is just to highlight that these are open simplices. And the dimension of these open simplices changes from 0 to the top dimension. Let's call the top dimension D. And you have a certain number of the I-dimensional simplex. So this is the I-dimensional simplex. So on the left-hand side, you have a bunch of already kind of spaced out simplices. And on the right-hand side, you have a bunch of spaced out simplices. The highest dimensional simplex here is D. The highest dimensional simplex there is D. And you have one additional constraint, which is that the Euler characteristic of this thing, which is the sum of all kinds of pluses and minus ones, is the same thing as the sum of those pluses and minus ones on the right-hand side. And then here's how the simplification process can go. Oh, sorry. This relation tells you that if you have, I know, something like a pyramid, you are allowed to cleave the pyramid in half. So you cleave it in half.
Just a generalization of what you had below.
Using a triangle, yes.
Yeah, look like this is not a very good way of cleaving it. This is probably a better way of cleaving it. So like, you know, you go through the midpoint of this side, and you go through that line, and you use this like half line, and you pull it apart, and you have an open pyramid here, and you have an open pyramid here, and this center open sheet is standing on its own.
Right.
So this was an open simplex cut into two open simplices and an open center that's also simplex. So magically, what used to be a single d-dimensional simplex is now two d-dimensional simplices, and a bit of garbage that you got here, which is lower dimension.
Yeah, generalization of what you had right below it.
Yeah.
So
This is why I'm saying that. Yeah, this is a consequence of that. This is a consequence of that. So you use a certain number of this magical doubling to make sure that you have the same number of d-dimensional simplices here, like m sub d is the same, and you have the same number of d-dimensional simplices on the left-hand side. And then once you have the equal number of dimensions, you may as well just forget about them. You can always move on, and you go down to the next dimension. And the only kind of complication that might happen is the following: that on one side, there was no d-1 dimensional simplex, but then somehow during this process, a d-1 dimensional simplex magically appeared. And then on the other side, you did nothing, and there is still no d-1 dimensional simplex. So the induction hypothesis is not satisfied. The induction hypothesis is the top dimensional simplices have to be there. But you can magically make a d-1 dimensional simplex pop up anywhere by using this relation.
Just be sure to split at least one thing on both ends, and
Exactly.
that'll be fine.
There you go.
Even if you don't.
So folks, this was a lot of fun. Let me tell you where this is going if you're interested. So many slides that I can speed through in such a way that I don't get embarrassed, and then you can still go home. Yeah, all kinds of statements about other semi-algebraic things. This is something I think that nobody has written down, including myself, that you look at the theory of real closed fields as opposed to definable sets. So the theory of real closed fields is made up of formulas. And so out of these formulas, the definable sets are represented by formulas, and the morphisms are represented by formulas as well. That's a distributive category. That too has the Grothendieck semiring, and that's the same thing as all its realizations over other kinds of suitable fields, where you restrict the coefficients to be rationals, for example. That's not even real closed. Or where you want the coefficients to be reals, or you want the coefficients to be other real closed fields. It has no measurable effect on the Grothendieck semiring, I'm pretty sure. This was actually needed, the fact that you only look at bounded semi-linear sets, because once again, that kind of isomorphism doesn't survive there. So in the semi-algebraic world, these two are isomorphic, because you have reciprocals and these kinds of things, but here they are not. And Schanuel announces the answer for semi-lin. Never mind, this is not important. Schanuel announces this answer for the semi-linear category. And here, you know, if anything jumps out to you, then you are very good. We all recognize this relation.
We'll add your ray.
I think Y is the ray. This is the fact that if you have a ray,
Yep.
if you have a ray, you're allowed to cut out a little interval and a point, and the rest is still just a ray.
Right.
So a ray is the same thing as interval plus point plus ray. This thing is something like you have an open ray, Cartesian product of open ray, and you halve it. And this is the same thing semi-linearly as a quadrant of a plane. This is the same thing, open quadrant as an open quadrant of a plane, and this is an open ray. So an open quadrant is open quadrant plus ray plus open quadrant. Turns out that you need to know this, but why is it that you don't have to know this in higher dimensions? So I think there's quite a bit of work. Schanuel kind of gives you a very beautiful and compressed argument, 2.5 lines, and says that this is obvious. So I think there's a lot of data mining there, and I'm just in the process of doing it, really.
All this in a 12-page paper.
I think it's just a dozen pages, and there's more to it. There's more in there as well. Okay, because Schanuel's functor is in the title, this is all due to Schanuel other than the notation. How is it that there is such a thing as dimension? One way to think about it is that if you have an n-dimensional thing and another n-dimensional thing, then the co-product of the two is still n-dimensional. So dimension wants to be valued in a kind of semiring that's idempotent, probably much more than just idempotent. But it turns out that just by playing with relations, it turns out that if you impose this single relation of additive idempotency, that has a lot of consequences. It's still an equational theory. You still have an adjunction. You can still fool with the explicit description of these functors and so on. And, you know, these are explicit formulas for what it means for them to be on this side, the analog of the Grothendieck thing.
What?
Say it again? I mean, if you want to stare at these relations and so on, it is just playing with formulas and everything, but it turns out that you have an explicit description of the reflector. So this is a right adjoint inclusion, and that's the reflector, that's a left adjoint. This is just like, you know, the Grothendieck functor from semirings to rings, except whatever, maybe the other way around. And it turns out that this is one way of constructing the associated idempotent semiring to a semiring. In terms of what kind of additional restrictions, what kind of quotients you have to introduce. And let me not spend any time on it. But one thing about, if you have the Grothendieck semiring, you look at the associated, the idempotent semiring, then that serves as a nice target for any kind of dimension counting measure, which satisfies, you know, these obvious properties. If you have any kind of dimension counting measure, you want the nothing to have the least dimension. You have the point, you have the unit dimension. You want it to be additive, multiplicative, and you want it to be additive. And so that is a universal example of a structure that accepts this kind of dimension count, and that's just a semiring. That really is just a semiring, and if you want to make it into a ring, it just goes away. The same way as, you know, the tropical semiring is a nice recipient of dimension, but you have to treat it as the tropical semiring. You can't do anything else to it. So I think it's Schanuel who advertised this notion as the right notion of dimension. But there's just one price, which is that this is not always linearly ordered. It's got a partial order on it, so some dimensions are comparable, but not all of them are. And I don't think there is a universal example of a linearly ordered dimension. So that would be interesting, because for example, for model theory and so on, Marley rank is a similar kind of construct for model theories that's very transfinite combinatorial and is like the right notion of dimension for abstract structures, but it goes along the ordinals. So it's automatically well ordered, not just linearly ordered. And it doesn't have this kind of universal mapping property. And as category theories really ought to love it. So what is it that you have dimension? Dimension is something that satisfies these axioms. What is it that there is a structure that's a kind of measure for dimension? Is in this case, the initial example of anything. And then maybe it's so complicated that you want to simplify it further, and you quotient it further, and you actually use something that's linearly ordered as the measure of dimension. But this intermediate object is fascinating, and I don't think it's been looked at great detail. For example, if you look at this presentation of semi-linear things, so what is the associated notion of dimension? This tells you that the infinite ray has its own dimension. It's sort of incomparable, that would be the y. That's incomparable to the x.
Right.
And so you have this partial ordering, right, of these things. And you kind of have to face the music, and there's the right notion of dimension that remains enough. And you can quotient it further. If you make the y equal to x, then this simplifies further, and you get the usual topological notion of dimension. But before that, it's already associated Schanuel semiring. Schanuel joins idempotent semiring that should be looking at.
Tibor, I gotta go, but you go on with them.
Thank you so much for your
No,
patience.
no.
I want to do something which